Hello, this is Marcus, and today I present an a priori model of information and intelligence, where the final goal is a machine superintelligence. This talk is somewhat technical, so parts may seem abstract. If that occurs, I ask that you pause the video and reflect briefly on the unclear points. Or you may consider replaying the video, as that may offer new insight as you find the mental maps needed to grasp this topic. Also, each slide is numbered at the bottom, so you can email specific questions and I am happy to reply. To start, this talk uses a philosophic term, a priori, which essentially asks what comes before information and intelligence. It thus implies study of non-intelligent and non-informational roles, with a hope of naming first principles for a computational model. I use 4 questions to frame those principles. 2 questions focus on the nature of information, and 2 focus on intelligence. The questions serve as steps in deconstructing what is often seen as a difficult topic. They reveal a continuous view of information and intelligence that allows us to consider the possible development of an adaptive machine intelligence or superintelligence. Similar questions exist in philosophy, where a large body of work exists as some 2,500 years of query and debate. They also point to what drives evolution by natural selection. But in our modern era, they mark a missing theory of meaning, named by Claude Shannon and Warren Weaver in 1949, at the dawn of the information age. As I focus on AI, or artificial intelligence, I refer to this missing theory of meaning rather than using more obscure philosophic terms. If we consider today's artificial intelligence, this question of meaning now has a different form. Computer scientist Edgar Dijkstra saw what had become a chronic problem in realizing major AI gains. He asked, "Does a submarine swim?" to stress the importance of a priori views and first principles in finding true progress. Dijkstra's challenge remains unanswered today and appears in many roles besides submarines that swim. Humanity now has a catalog of first principles that drive advances on many fronts. Comparing those modern advances to their early roots evokes Arthur C. Clarke's third law of sufficiently advanced technologies indistinguishable from magic. A seemingly fantastic human inventiveness marks a potent creative capacity. Despite eons of adaptation, we still struggle to understand that creativity. We see many material, scientific, neurological, and psychological facets, but none that cover inventiveness in a clear way. Recent AI efforts seek to imitate the brain's activity via computer neural nets and the like, ignoring Dijkstra's critique on submarines that swim. Thus, in some circles, this issue is now called the hard problem, but where an information theory solution is still thought to be possible. Detailing adaptive human creativity in a general theory of meaning is this talk's purpose. To initiate that theory, I start with the first of the 4 questions: what comes before information? This is often seen to imply a body-mind problem or a dual material aspect. Much literature exists on dualism that I do not cover here. Instead, I ask that you see the paper noted at the talk's end for that detail. In place of a dualist view, I use a more basic approach. I ask, when does something we might call information first arise in the cosmos? If we see the Big Bang as a valid scientific theory, we also accept that after some 200,000 years, the cosmos holds only pre-photonic plasma as an early thermodynamic maximum or entropic symmetry. That early cosmos is so uniform that it conveys only an unbounded and undifferentiated vastness where no information is possible. But later, condensate starts to arise in that plasma. Imagine that just one such condensed object arises as a minimal case. Does that one object convey information? The object's solitude leaves it unobserved and non-functional. No witness can verify its existence, and a lack of material counterparts precludes any functional role. The object may be logically possible, but its isolation prohibits any chance of useful data. To whom and to what end would that data be sent and used? With no functional counterparts, the object's existence is inconsequential. As a next step, early cosmic condensate actually has many leptons and quarks variably popping in and out of existence. We can then ask, do many chaotic objects convey information? Material existence is now more plain, but we cannot truly differentiate one object from another. Endless variability in object and object status prohibits the chance of any sense-making. Those chaotic roles are far removed from the cosmos we now see as regularly interacting atoms, gas clouds, stars, solar winds, orbital masses, and the like. As a last step, prior views imply that only if at least two reliable objects in reliable interaction occur does functioning or material significance arise. Only then do we see something we can call order, homeostasis, or non-chaotic data. We start with an energetic cosmos of pure noise and no useful data, but later see informational signs, as with Shannon's signal entropy. Signal and noise indeed cohabit all material and organisms in the cosmos to varying degrees. Signal and noise thus also drive evolution by natural selection in testing diverse functional roles. Alternatively, we can say signal and noise variability, or entropic mediation, is the main cosmic activity. Lastly, signal integrity becomes imperative via natural selection, since extinction is the only logical alternative to reliable signals. Next, if we study what a signal entails, we see two traits: objective elements in functional roles. We might then say a dual material state exists. But this model goes beyond dualism, and a closer look is needed. For material properties, we actually see two material objects in one functioning role, as a dualist signal with three true facets. The roles are also conjunct. Removing either object from this signal causes the subject role to vanish. Also, removing a subject role collapses two objects to one in a parallel manner. Minimal informational signals thus imply a unified triad or a dualist triune role. Next, if we study a signal's logical properties, another trait arises. The prior object and subject roles support reliable signals, but subject-object variability drives evolution and adaptation in a highly variable cosmos. If only fixed roles exist, evolution and adaptation are impossible. This means an adaptive dualist triune exists alongside a material dualist triune, where all roles jointly co-evolve as signal or devolve to noise. A full dualist triune view thus has matter set in space-time that is energetically entangled. Lastly, lessening this minimal informational state returns us to the earlier non-informational state. To answer the first question, in exploring what comes before information, we see a dualist triune role. Going forward, I call this a subject-object or SO model. With the first question now answered, we go on to the next question. What is meaningful information? Meaning has many facets, but as this is an a priori study, I focus on key roles. To start, I reframe the question to include what the earlier study revealed. I ask, how does a dualist triune support meaningful experience in the world, often called consciousness? Further, with signal integrity as imperative, I also ask if that experience supports survival. The earlier analysis set noise and signal as logical endpoints, with SO variability mediating between those points. Durable experience in a variable cosmos thus implies growing utility. Here, time conveys another dualist triune role. Now marks the immediacy of material events, and memory as a record of past events drives an imagined future. An agent's sense of time as memory is then tested on the evolutionary landscape. In a parallel way, height and width hold the immediacy of now, while depth supports imaginal facets as a past and a future. A joint dualist triune thus marks an experiential role that broadly frames survival on the evolutionary landscape. If we examine other SO models, like the standard model in physics and the periodic table, matter also appears in a triune role. As such, initial fundaments for every agent on every landscape are framed here and begin detailing a general adaptive continuum. Lastly, key to those interrelating triune fractals is the bridging role levers hold as a natural engine and as yet another dualist triune with mechanical and biological traits. A lever's bridging role supports the unfolding of an even larger evolutionary landscape, as soon seen. Thus, Meaning is reductively framed here as a core sense of space, time, and matter. But again, meaning has many sides, so a more complex view is also needed if we are to define intelligence. To show growing complexity, I return to the ordered bits. SO models seen as innately objective mark a composite role, or an objectified subject state. The standard model in physics and the periodic table are good examples of objectified models. Composite roles then afford new gains as they offer a new objective base for later SO trials in a scalable manner. Here, bits typical to computers convey an objective base that must be interpreted. In SO sensemaking, various bit lenses can be used to find a functional match or fitness. Fitness thus applies equally to machine interpretation, agent interpretation, and evolution as a minimally scalable role. Posited fits are then tested on the evolutionary landscape. Here, ASCII code standards denote the landscape and what is seen as useful in supporting further scalable advances. Certain lenses, agents, or designs fail at this sense-making task of fitness, while others succeed, all of which later supports selectable survival in a scalable manner. This higher-order interpretive scenario completes the answer to what is meaningful information. It does so by extending the earlier dualist triune to a scalable role, with no upward limit. With the second question now answered, I focus on the third question: how is adaptive logic generated? To answer this question on the generation of logic, we must first grasp the meaning of adaptive logic. Earlier, I stated levers are a natural engine that shifts space, time, and matter, and with mechanical and biological facets that afford scalable evolutionary advances. In a mechanical role, levers are one of 5 simple machines that underpin a vast material infrastructure. In a biological role, levers pervade life. Levers as endo and exoskeletons arise in many agents as fitted fulcrums or joints. Rolling fulcrums are then seen in snakes, worms, plants, and the flagella and cilia of microbes. Levers mark a near-universal function that underpins almost every act to explore and exploit the evolutionary landscape. Levers are thus nearly always present and known to agents as a minimal, general adaptive logic. Lastly, agents never need to invent a lever, since levers are given as order for free, innate to much of life. Universal lever logic demands close study if we are to fully grasp adaptive logic. First, levers mark another dualist triune role as fulcrum, effort, and load elements. Second, levers arise as 3 types: Class 1, Class 2, and Class 3. Third, a lever's innate variability marks another triune role, tied to signal entropy, as soon seen. As a whole, these 3 entangled triunes further stress the presence of a fractal or scalable continuum. Next, to show adaptive logic, I differentiate variability in levers from basic lever functioning. A functioning lever is a set of elements that jointly convey signal entropy, shown here as a lever object. This lever object is thus functional but non-adaptive, as all the elements are fixed. While this lever is functionally dynamic, it is not flexible or dynamic enough for it to be adaptive. Adaptive logic arises only if lever elements shift in specific ways. Such shifts reinvent a lever and make it suitable for new roles. A simple shift is shown here for a load element. This shift is gradual and affords minute optimization as evolution by natural selection. This unfolding of adaptive logic as element roles within levers initiates yet another dualist triune. Lastly, to preserve a required link to signal entropy, I call this gradual variability value entropy. Next, that gradual adaptive logic expands if the order of elements changes. Here, new lever orders arise if the load jumps to a new region. This adaptive growth is mildly disruptive and has 2 facets. 1. A new order in lever elements affords a new lever type. And 2. The prior value entropy likewise extends to those new orders, as a 3-fold increase in total adaptivity. Again, To maintain a link to signal entropy, I call this mildly disruptive change order entropy. It is mildly disruptive as no new elements are needed for novelty to arise, while also affording a major shift in overall adaptive capacity. Thus, value entropy and order entropy jointly imply many discoverable possibilities or adaptive options, shown here as diverse mechanical tools. In evolutionary biology, discoverable options give rise to great variety in species, which frames an ongoing debate on the nature of evolution as gradual versus punctuated. A full account of entropic variability in diverse roles exceeds what this talk can cover. Instead, more detail is referenced in the paper listed at the talk's end. As a third entropic type, adaptive options explode if new elements arise. Here, 0 points show where lever logic fails and something else occurs. That something else is a new element that devolves from the prior lever system. The emergence of new elements then affords a chance to discover new element sets, or new tools and functions. Element entropy is acutely disruptive and relies on an agent's ability to find new element sets, seen in humans as the development of simple machines and more. This entropic role is the least innate of all three roles, and relies on learning seen in prior adaptations. Again, a full account of this entropic evolution exceeds what this talk can cover, and is instead referenced in the paper listed at the end. This unfolding of adaptive logic via three entropic steps marks another dualist triune role. To summarize those roles, I show them in a joint generative capacity, bridging noise and signal. It marks a type of informational work driving adaptive logic and producing many adaptive options. With the first three questions answered, we now move on to the last of the four questions. How is adaptive logic optimized? The prior analysis shows adaptation creating numerous adaptive possibilities. Next, we must see which options best support survival in a selective manner. But natural selection is innately ambiguous and presents a major hurdle. First, the adaptations from that prior analysis are numerous and implies each option must be tested against all others, an enormous computational task. Second, to think that an optimal role exists is suspect. For example, time is often crucial where expediency is preferred to ideal solutions. Third, energetic variation in natural selection can be vast. For example, a reductive view of energy and force has 16 forms of energy and 4 fundamental forces, not all of which we fully grasp, and all operating jointly. The often impromptu nature of space, time, matter, and energy around any selection event can alter preferred outcomes from moment to moment. As such, happenstance is a central selection factor, lessening the chance for optimal roles. Happenstance seems to preclude orderly selection of any sort, except for two curious facts. First, chaos theory is known to have some capacity to model complex natural events. Second, in studying the evolutionary landscape, more dualist triune roles arise. Here, I show classic threefold selection pressure as a dualist triune form, and classic agent responses also hold a dualist triune form. These naturally opposed roles can then be joined to present a simple reductive model I call selection dynamics. The implication of selection dynamics and chaos theory is that other informational or computational universals may also exist that can lessen the ambiguity innate to selection as happenstance, but more research is needed to detail any such universal forms. Well, with all four questions now answered, this talk comes to a close. Each of the four questions are explored in more detail in papers referenced in the one main paper listed here, all of which are available at the link shown. Also, my email address is given if you have questions I might answer. Thank you for your attention.